There are two cheap metals that millions of gardeners are burying in their beds right now. The videos promise they end every pest problem you have permanently for under $20. The Amish are said to have guarded this method quietly since the 1860s, and the laboratory numbers behind it look almost too good to be real. One controlled test recorded a 92% drop in the pests crossing the barrier. So a respected institution decided to test the exact same method in a normal backyard garden. What they found in real soil was the opposite of what every viral video had been claiming, because there is a real science of repelling insects with metal, and it is genuinely astonishing. But it looks nothing like the penny and nail trick spreading across the internet right now. By the end, you will know exactly which part is real, which part is a myth, and what to do instead. The cabbage leaves look like someone held them up to a light and punched holes through them with a pen. Whatever did this was methodical, working from the outer edge inward, and by the time you notice the damage, the plant is already half gone. This is the scene that greets gardeners across the American Northeast and the English Midlands every single summer, and it has been greeting them for as long as people have grown food. Pull back the leaf, and you will find them. Small, soft-bodied, clustered so tightly they look like a smear of gray-green paint along the central vein. Aphids feed by piercing plant tissue and drinking the sugar-rich sap moving through it, and a single mature female can produce as many as 80 offspring in 1 week without mating. The mathematics of that reproduction rate are genuinely staggering when you watch a colony that was a dozen insects on Monday become several hundred by the following weekend. Walk 3 rows over, and the squash are in even worse shape. Squash bugs, flat and shield-shaped, press themselves against the underside of leaves in rows so neat they appear almost deliberately arranged, and the damage they cause is not gradual. They inject a toxic compound into the plant tissue as they feed, which causes the leaves to wilt suddenly and completely, a symptom extension entomologists in Pennsylvania call Anassa wilt, after the bug's genus name, and it can take a healthy plant from vigorous to dead in under a week. Here is the thing. Most gardeners who reach this point have already tried something. The garage shelf tells the story on its own. There is the bottle of pyrethrin spray from 2 summers ago, still half full because it burned the beneficial insects along with the pests. There is the neem oil concentrate that worked inconsistently and smelled so strongly that neighbors in Chicago and Manchester alike have complained about it. There is the row of yellow sticky traps that caught everything except the insects actually destroying the crop. Each of these represents money spent and optimism exhausted, and the feeling that accumulates across several seasons of this is not anger exactly, but a specific, grinding fatigue. That fatigue is important to understand because it is precisely the emotional state that makes a certain kind of promise irresistible. When you have sprayed and trapped and manually removed pest by hand for 3 or 4 years running, the idea of a one-time fix that costs less than a restaurant lunch and never needs repeating does not sound like wishful thinking. It sounds like relief. The videos that carry this promise understand that feeling intimately, and they are engineered to meet it at its most vulnerable point, which is the moment you are standing in the garden at sunrise, looking at damage you did not prevent. The promise arrives wrapped in authority. It does not come from a faceless corporation selling a product, which would immediately raise suspicion. It comes, the videos tell you, from a community of people who have farmed the same land in Lancaster County, Pennsylvania, for generations without synthetic chemicals, and whose gardens are, by any observable measure, genuinely productive and healthy. The Amish are real, their agriculture is real, and their results are real. What the videos do with that foundation is a more complicated story, and it starts with a beetle and 2 strips of copper buried in the ground. What no one in those videos stops to ask is a question that turns out to matter enormously. How much of what those Lancaster County gardens actually do can be explained by 2 metals, and how much of it is explained by everything else those farmers do every single day? The answer to that question will change what you buy, what you bury, and what you do instead this season. But before you get to the answer, you need to understand exactly how convincing the claim is, because the numbers attached to it are the kind that stop you mid-scroll and make you reach for your wallet. 92%. That figure is sitting in your mind right now from the opening of this video, and it is a real number from a real set of tests. The story of what those tests actually measured and what they did not measure, and what a garden realistic study found when it repeated the experiment in actual soil with actual rain and actual slugs, is one of the more instructive gaps between a laboratory and a back garden that you will ever encounter. And it begins not in Lancaster County, but in a French vineyard in the 1880s, with a scientist who noticed something strange about the vines growing along the road. Lancaster County sits in the southeastern corner of Pennsylvania, and on a clear morning in late June, the fields there look like something a landscape painter would invent rather than find. The rows are straight, the soil is dark, and the farms are productive in a way that draws agricultural researchers from universities in Philadelphia and beyond to study what is actually happening at ground level. This is not a romanticized version of a place. The productivity is documented, measurable, and in several peer-reviewed comparisons with conventional neighboring farms, genuinely impressive. What the Amish practice in Lancaster County is not one thing but a layered system built from several disciplines working simultaneously. Crop rotation is applied rigorously, moving plant families around the beds so that soil-borne pests and pathogens that target one species cannot build up in a fixed location across multiple seasons. Composting returns organic matter to the soil in volumes that conventional operations rarely match, feeding the microbial communities that make nutrients available to plant roots. Diversified plots where many different species grow in proximity rather than a single crop covering an entire field create the kind of habitat complexity that supports predatory insects alongside the pests those insects consume. Here is the thing. Every one of those practices has a substantial body of extension and peer-reviewed research behind it. The University of Pennsylvania and Penn State's College of Agricultural Sciences have both documented the effectiveness of integrated, low-input approaches of exactly this kind. None of that documentation requires a metal buried in the soil to explain the results. The genuine Amish agricultural system is, in purely scientific terms, already a complete answer to the question of why those gardens thrive. What the viral videos do with this foundation is a specific and quite sophisticated move. They borrow the credibility of a real community and a real set of results, and they attach to it a mechanism that the community itself does not universally endorse, and that the research record does not support in the form being claimed. The result is a claim that is almost impossible to argue against in a comment section, because any pushback against the metal theory can be deflected by pointing to the undeniable fact that Amish gardens are genuinely productive. The productivity is real. The explanation being offered for it is a separate matter entirely. Beyond that, the videos introduce a figure, a named Amish farmer, usually placed in Lancaster County, whose specific results with buried copper strips are described in vivid detail. The potato beetle story is the most common version, and it is worth examining closely because it is constructed with real craft. A specific pest, a specific crop, a specific placement of a specific material, and a specific outcome measured over a specific number of seasons. Each detail adds a layer of concreteness that makes the account feel like testimony rather than invention. That feeling is doing a great deal of work. What makes this narrative device so effective is that it exploits the way human memory evaluates evidence. Psychologists at the University of Michigan have documented repeatedly that a single vivid, named concrete account registers as more persuasive to most listeners than a statistical summary, even when the statistical summary represents data from thousands of observations. A farmer named Eli, standing in his Lancaster County field with healthy potato plants, defeats a confidence interval in the gut-level calculus that most viewers apply without knowing they are applying it. The videos are not naive about this. They are precise about it. The honest version of this story, which is the one worth telling, actually makes the Amish example more interesting rather than less. A farming community that achieves genuine pest resilience without synthetic inputs is doing something worth understanding in granular detail, because the methods that actually account for their results are transferable, scalable, and supported by research that any gardener can access. The metal story, by contrast, offers a shortcut that substitutes a one-time installation for the ongoing practice that produces the actual outcome. Shortcuts of that kind have a consistent track record in agriculture, and it is not a flattering one. You won't believe this, but the most telling detail about the Amish copper secret as it circulates online is not in any of the claims it makes. It is in the language those claims use. The same phrases, the same sentence structures, the same specific details recur word for word across dozens of channels and blogs that have no stated connection to one another. Brother Yoder showed me this in the summer of 1991. The agent from Penn State called it the most significant find in his 30 years. These lines do not vary because they were not independently observed. They were copied. And that mechanical repetition, invisible to a first-time viewer, is the single most reliable signal that what you are reading is content farming rather than documentation. That does not mean the underlying question is uninteresting. On the contrary, the question of whether metals in or around garden soil can influence pest behavior is genuinely fascinating, and the scientific record on it is far stranger and more dramatic than anything the viral versions have invented. The answer begins with slugs, a strip of copper and a gap between laboratory conditions and a garden in the rain that no content farm has ever bothered to mention. Picture the Colorado potato beetle for a moment before accepting any claim made about it. It is a striking insect, roughly the size of a fingernail with a domed shell striped in alternating lines of cream and black that make it look almost decorative against the dark green of a potato leaf. It does not crawl tentatively. It feeds with a confidence that seems almost contemptuous, stripping foliage down to bare stems with a speed that can devastate a mid-season crop in under 2 weeks. Farmers in Lancaster County, Pennsylvania, and in agricultural districts across the English Midlands know this insect by its damage before they ever see the insect itself. The viral story places a farmer, call him Eli, in his Lancaster County potato field sometime in the early 1990s. He buries 2-inch strips of copper flashing around the perimeter of his beds, pressing them into the soil so that roughly 1 inch protrudes above the surface. Within a season, the story goes, his potato beetle problem collapses. His neighbors, using conventional methods, continue to fight the pest. Eli does not. The copper, the videos explain, produces a mild electrical charge when it contacts the moisture in the soil, and that charge disrupts the beetle's nervous system as it attempts to cross the barrier. Every element of that mechanism has a specific problem, and the problems are worth laying out clearly because they are not minor quibbles. They are the difference between a method that works and one that costs you a season. The Colorado potato beetle is a flying insect. It does not approach your potato plants by walking across the soil from a distant location. It flies in, lands directly on the foliage, feeds, and lays its eggs on the underside of the leaves it is already standing on. A perimeter barrier, copper or otherwise, placed at soil level presents no obstacle whatsoever to an insect that arrives from above. What's more, the electrical mechanism described in these videos does not survive contact with basic physics. A strip of copper buried in moist soil will develop a small electrochemical potential, particularly if a dissimilar metal is nearby, but the voltage produced by a penny and a galvanized nail in garden soil is measured in fractions of a volt under the most optimistic conditions. The Colorado potato beetle has a nervous system that tolerates far greater electromagnetic variation simply by living outdoors near power lines, electrical fencing, and the natural electrical charge of the atmosphere during a thunderstorm. The idea that a fraction of a volt at soil level disrupts a flying beetle's approach to a plant 2 feet above that level is not supported by any published entomological research. Here's the thing. Researchers at Cornell University's Department of Entomology have documented the Colorado potato beetle's resistance mechanisms in considerable detail. And what those documents describe is a pest so behaviorally and genetically adaptable that it has developed resistance to more than 50 individual insecticide compounds since the 1950s, more than any other agricultural pest species on record. An insect with that adaptive profile, crossing that barrier by air, is not stopped by a buried strip of any metal. The copper story for beetles is not, however, a complete fabrication in every direction. Copper does have a genuine, documented, moderate repellent effect on a specific category of pest, and the mechanism behind that effect is real, measurable, and has been replicated in controlled conditions. The pest category is mollusks, slugs and snails. The mechanism involves the reaction between copper ions and the glycoprotein mucus that slugs and snails produce for locomotion, and the result is a genuine aversive response that has been captured on camera and quantified in laboratory settings. That is a real phenomenon, and it deserves to be treated as one. But the slug story is also more complicated than the viral version presents, and the complication arrives in the form of a study conducted in an actual garden rather than a controlled laboratory environment. The Royal Horticultural Society, one of the oldest and most rigorous horticultural research bodies in the English-speaking world, published results in 2023 from a carefully designed test of copper tape alongside 4 other commonly recommended slug barriers: mulch, eggshells, grit, and wool pellets. The test was conducted in realistic outdoor conditions with real soil, real weather, and real slug populations. None of the 5 barriers produced a statistically significant reduction in slug damage to the plants they were supposed to protect. That result sits in direct tension with the laboratory numbers, and that tension is the most honest and most useful thing this video can offer you. A controlled lab test with 2-inch copper tape recorded up to 87% prevention of slug crossings under dry conditions. A 4-inch tape reached 92% against small slugs. Those numbers are real. And yet in a garden, with rain patching the copper surface and organic debris bridging the gap and adult slugs larger and more motivated than laboratory specimens, the barrier failed to produce a measurable outcome. Understanding why those 2 results coexist is the key to everything that follows. Watch a slug approach a copper strip in a dry laboratory setting, and you will see something genuinely strange. The animal moves forward at its usual pace, contacts the copper surface with the leading edge of its foot, and then recoils. Not dramatically, not violently, but with a definite and repeatable change of direction that looks, for all the world, like a decision. The slug does not cross. It turns, moves along the barrier's edge, and eventually retreats. Film this encounter 100 times under controlled conditions and the pattern holds with enough consistency to produce the numbers that ended up in the research literature. The mechanism behind that recoil is electrochemical rather than electrical, in the simple sense that the viral videos imply. Slug locomotion depends on a continuous layer of glycoprotein mucus, a substance rich in water and dissolved ions that the animal secretes and moves across simultaneously. When that mucus contacts a copper surface, copper ions dissolve into the mucus layer, and the resulting reaction generates a small but detectable change in the electrochemical environment at the slug's foot. The experience for the slug appears to be aversive, comparable in effect if not in mechanism to the sensation a bare human foot experiences touching a mildly charged surface. The slug does not receive a shock in the voltage sense. It experiences a chemical disruption at the tissue interface that it consistently chooses to avoid. California's Integrated Pest Management Program, one of the most rigorously maintained extension resources in the United States, has quantified how this effect scales with barrier width. A 1-inch copper tape strip produced 68% prevention of crossings in their documented tests. A 2-inch strip reached 87%. A 4-inch strip hit 92% against small, newly hatched slugs. Those figures are where the 92% claim in the viral videos originates, and they are legitimate numbers from legitimate testing conditions. The problem is not that the numbers are wrong. The problem is the gap between those conditions in your garden on a Tuesday morning in October. Beyond that gap lies a list of failure modes that the viral videos never mention, because each one would require the viewer to do something more complicated than bury a strip and walk away. Adult slugs are substantially larger and heavier than the newly hatched specimens used in the most favorable lab test, and their greater body mass means a proportionally smaller area of their foot contacts the copper surface at any moment, reducing the intensity of the electrochemical reaction. Rain, which occurs in most gardens where slugs are a problem precisely because slugs require moisture to thrive, washes copper ions from the tape surface and accelerates the formation of copper oxide patina, a greenish layer that dramatically reduces ion transfer. Organic debris, a single fallen leaf or a tendril of plant material touching both sides of a barrier, creates a bridge that slugs navigate without contacting the copper at all. The Royal Horticultural Society test in 2023 did not use unusual conditions designed to make barriers fail. It used a normal English garden with normal English weather and normal slug populations, which is to say wet, variable, and populated by Arion vulgaris, the Spanish slug, now the dominant slug species across much of northern Europe and increasingly common in the northeastern United States. Arion vulgaris is larger, more aggressive, and more reproductively prolific than the native slug species the earlier laboratory studies used. Against this animal, in this environment, copper tape performed no better than an untreated control. Neither did eggshells, grit, mulch, or wool pellets. A separate semi-field study which split the difference between a laboratory and an open garden by using enclosed outdoor plots tested copper foil against water glass, which is sodium silicate solution painted onto a surface to create a dry, crystalline barrier. Copper foil delayed slug passage in this setting, but did not prevent it. Water glass completely blocked slug movement across the treated surface for the duration of the trial. That result has not appeared in a single viral video about garden pest control, almost certainly because sodium silicate costs roughly the same as copper tape, requires no romantic historical narrative, and cannot be connected to a story about Amish farmers or buried metals producing an invisible field across your beds. What's more, the failure of copper tape in realistic conditions is not an argument against using copper in the garden at all. It is an argument for precision about what copper actually does, where it does it, and under what conditions its effect is strong enough to matter. A clean, wide copper barrier around an isolated container or a raised bed with no plant bridges, checked and cleaned regularly, still offers a genuine, if partial, line of defense against small slug populations in drier periods. That is a real tool used correctly. It is a substantially smaller and more conditional tool than the viral version describes, but it is real, and that distinction is exactly the kind of honest information that allows a gardener to make a decision that actually improves their harvest. The mechanism that the videos describe for beetles, the mild shock traveling through soil and disrupting an insect's nervous system at a distance, is a different category of claim entirely. And it points toward a genuinely fascinating area of research that the content farms have never accurately described. Electric fields can repel insects. The documentation of that effect spans 82 species across 17 different insect orders, and the underlying science is some of the more surprising material in applied entomology. But the system that produces a field strong enough to matter looks nothing like a penny and a nail in the ground. And the gap between what works in a research greenhouse and what a buried coin produces in your soil is so large that it changes the entire conversation about what you should actually be doing this weekend. In the summer of 1994, according to dozens of videos, blogs, and gardening forum posts that have accumulated across the internet over the past decade, researchers at Cornell University conducted a controlled study of copper barriers against garden pest and recorded a 96% reduction in pest crossings. The study is cited with the confidence of settled science. It is referenced by name, by institution, by year, and occasionally by a journal title that shifts slightly from one citation to the next. There is one significant problem with every one of those citations. No verifiable version of that study exists in Cornell's published research record. Search Cornell University's digital repository, the university library's agricultural research archive, or any of the major peer-reviewed databases that index entomological literature from that period, and the 1994 copper barrier study producing a 96% figure does not appear. What does appear, across multiple legitimate sources, are the California IPM numbers already described in this video. 68% for 1-inch tape, 87% for 2-inch, 92% for 4-inch, all against small slugs under dry laboratory conditions. Those numbers are real and citable. They are also consistently cherry-picked at their highest value and presented without the conditions that produce them, which is a form of misrepresentation even when the underlying number is genuine. The invented citation matters for a specific reason that goes beyond fact-checking as an intellectual exercise. When a viewer encounters a study attributed to a named institution in a specific year, they perform an unconscious credibility transfer. Cornell is a real university with a genuine agricultural research tradition stretching back to the 1860s. The viewer does not go and search the archive. They extend to the claimed study the credibility they have already assigned to the institution. And that borrowed authority is what makes the claim stick across subsequent viewings, shares, and comment section defenses. The fictional citation is doing more persuasive work than any of the other elements in the video, and it does it invisibly. However, the genuinely astonishing thing about this particular gap between the viral claim and the research record is that the real science in this neighborhood is more dramatic, not less. The documented effect of electric fields on insect behavior is one of the more surprising bodies of literature in applied entomology, and it begins not with garden slugs but with mosquitoes, and a question about charged particles in the air. Researchers studying insect avoidance of electrostatic environments found that mosquitoes exposed to charged particles in their flight path showed consistent and repeatable avoidance behavior, and that uninsulated copper and aluminium conductors carrying an electrical charge produced measurable repellent effects against flying insects in enclosed test environments. What's more, a systematic review of published literature on insect responses to electric fields identified documented avoidance behavior across 82 species in 17 different insect orders. That is not a narrow finding about one pest in one setting. It is a pattern broad enough to suggest that sensitivity to electric fields is a widespread feature of insect neurology rather than a quirk of a single species. The Amish intuition, or more accurately, the intuition that the viral videos attribute to Amish farmers, that something about electricity in the soil or around the plant matters to insects, points in a direction that genuine research has also explored. The direction is real. The destination the videos describe is not. High-voltage electric field screens, powered systems that maintain a sustained and significant charge across a physical barrier, have been tested in greenhouse environments and shown to exclude flying insects, fungal spores, and pollen with considerable effectiveness. These are not penny and nail systems. They require a power source, insulated mounting structures, and voltage levels measured in thousands of volts rather than fractions of a single volt. The gap between a functional electric field exclusion system and a buried coin next to a galvanized nail is not a matter of degree. It is a categorical difference between a technology that does what the videos promise and an arrangement of objects that produces no meaningful field at the scale of a garden pest's nervous system. Just imagine what the comment sections on these videos would look like if the viewers who spent $25 on copper tape and galvanized nails knew that the genuine version of the technology they were trying to approximate costs several $100s, requires a continuous power supply, and was developed in controlled greenhouse research rather than in a Lancaster County field. The gap between the viral promise and the actual science is not a gap that discourages the underlying curiosity. It is a gap that redirects it towards something that genuinely works, and that redirection is the most useful thing this video can offer anyone who arrived here because their cabbage looked like Swiss cheese on a Monday morning. At the same time, the most important question this evidence raises is not whether copper tape works, because the honest answer to that is sometimes, partially, under specific conditions. The most important question is what the gardeners who genuinely solved their pest problems over many seasons actually did, and whether any of it is as simple and inexpensive as the viral version promises. The answer to that question turns out to be yes, with a qualification. The methods that work reliably are simple and inexpensive, but they require understanding the specific biology of the pest you are fighting rather than installing a single fix and expecting it to address every insect that arrives in your garden. That understanding begins with knowing what each pest actually is, how it actually moves, and at what point in its life cycle it is most vulnerable to disruption. The viral videos make a specific and very confident claim about duration. Bury the copper correctly, they say, and you will not touch it again for 19 years. Some versions push the figure to 25. The number varies slightly from channel to channel, but the core promise is consistent. This is a one-time installation, A permanent solution, a thing you do once on a weekend in April and never think about again while your neighbors are still spraying and trapping and losing sleep over their squash. That promise of permanence is doing as much emotional work as the pest reduction figures, possibly more, because the gardener, who has spent 5 seasons fighting the same insects, is exhausted not just by the cost, but by the repetition. Here is what copper actually does when you leave it in soil or mount it on a raised bed frame across 19 years of weather. Within the first several weeks of outdoor exposure, the clean reddish surface of fresh copper begins oxidizing. A thin layer of copper oxide forms first, darkening the surface to brown. Over months, particularly in wet climates like those of the English Midlands or the Pacific Northwest, that oxide layer gives way to a more complex patina composed of copper carbonate and copper hydroxide, the greenish coating visible on old copper roofing and on bronze statues in cities like London and Boston. This patina is chemically stable. It is also substantially less reactive with slug mucus than clean copper metal, because the ion transfer that produces the aversive response in the slug depends on fresh copper ions dissolving from an unoxidized surface. What this means in practical terms is that the effectiveness of copper barriers is inversely related to their age in outdoor conditions. A brand new strip of copper tape in its first dry season performs closest to the laboratory ideal. The same strip, after 2 or 3 years of rain, frost, and organic debris accumulation, performs substantially below that ideal, and a strip that has spent 19 years in the ground performs at a level indistinguishable from an inert object of similar dimensions. The lasts forever claim is not just unsupported. It is contradicted by the basic chemistry of copper oxidation, which is documented in materials science literature and visible to anyone who has watched a copper penny darken over a decade. The true history of copper in plant protection is, however, genuinely dramatic, and it requires no invented archive to tell it well. In the autumn of 1879, a French botanist named Pierre-Marie Alexis Millardet was walking through the vineyards of the Médoc region near Bordeaux when he noticed something striking. The vines growing along the public road were visibly healthier than those deeper in the vineyard, their leaves free of the gray-white mold of downy mildew that was at that moment devastating French wine production. Millardet stopped and asked the vineyard workers why the roadside vines looked different. The answer was practical rather than scientific. The workers had been painting the roadside vines with a visible mixture of copper sulfate and lime to deter passing travelers from eating the grapes. The treatment had no intended agricultural purpose. It was a theft deterrent. But the copper mixture, applied to the leaf surface, had accidentally created one of the most effective fungal disease controls in the history of plant agriculture. Millardet spent the next several years refining the formula, and by 1885 he had published the results of his systematic trials, introducing to the world what became known as Bordeaux mixture, a copper sulfate and lime spray that remained the primary defense against grape downy mildew for decades, and is still used in certified organic viticulture today. That origin story is cinematic in a way that no invented Penn State archive can match, and it establishes something genuinely important about how copper functions in plant protection. Millardet's discovery worked because the copper was applied directly to the plant surface where the pathogen made contact, in a soluble form that maintained reactivity across a growing season when reapplied regularly. The mechanism was contact and chemical reactivity, not a field emanating from a buried strip. The lesson the real history teaches is almost the opposite of what the viral videos draw from it. Copper works when it is where the problem is, in the form that stays chemically active, reapplied as conditions degrade its surface. As a result, the genuine descendants of Millardet's discovery are the copper-based fungicide sprays that remain available to organic gardeners today, used against fungal diseases like late blight on tomatoes and downy mildew on grapes and cucumbers. These products work within a documented mechanism, require regular reapplication to maintain effectiveness as rain washes the surface and new growth emerges untreated, and have a body of replicated trial data behind them. They are not romantic. They do not promise a one-weekend installation and 19 years of relief. But they address a real problem through a real mechanism, which is a more durable kind of satisfaction than the alternative. Even stranger than the gap between the viral promise and the real history is what the viral videos leave out entirely when they discuss copper's permanence. The gardeners who report the best long-term results with copper barriers are not the ones who buried the metal and walked away. They are the ones who cleaned the tape seasonally, replaced degraded sections, maintained clear gaps between the copper surface and any plant material that might bridge it, and used the barrier as one component of a broader management strategy rather than as a standalone fix. Their results are real. Their method is simply not the method being sold. The second metal enters the story quietly, almost as an afterthought in the earlier versions of the viral videos, but in the more recent iterations it has been elevated to equal billing with copper. Zinc, the videos explain, is the missing half of the system. Copper alone produces a barrier. Copper and zinc together, placed in proximity in moist soil, produce something categorically different: a tension field, an invisible zone of electrochemical activity that extends outward from the metals and influences the behavior of insects throughout the entire garden rather than just at the point where a pest contacts a physical strip. The German word Spannungsfeld, meaning tension field or voltage field, is deployed in several versions of this claim to give it a technical weight that the English equivalent somehow lacks. The galvanized nail is the delivery mechanism for the zinc component. Galvanization is a real industrial process in which steel is coated with a layer of zinc to prevent rusting, and galvanized nails are genuinely inexpensive, available at any hardware store in London or Chicago or a rural Pennsylvania farm supply, and do contain zinc on their surface. So far, so real. The videos then instruct the viewer to place galvanized nails at intervals around or within the garden in proximity to the copper elements, and explain that the combination of the two metals in moist soil creates a galvanic cell, essentially a battery, that generates a continuous low-level electrical field across the growing area. This field, they claim, disrupts insect navigation, feeding behavior, and reproduction at a distance, without any direct contact between the insect and the metal. The galvanic cell part is, in isolation, physically accurate. Two dissimilar metals in an electrolyte solution, which is what moist soil partially approximates, do generate a small voltage through the electrochemical reactions at each metal's surface. A copper-zinc galvanic cell in ideal laboratory conditions produces approximately 1.1 volts. In garden soil, with its variable moisture content, organic matter, and competing ion concentrations, the actual voltage produced is considerably lower and highly inconsistent, dropping further as the metal surfaces oxidize and as the soil conditions fluctuate with rainfall and temperature. The garden as battery metaphor is not entirely wrong as a description of the chemistry. It is catastrophically wrong as a description of the effect. What the videos never address is the question of field strength at distance. The voltage produced by a copper-zinc galvanic cell in garden soil generates an electric field that diminishes with the square of distance from the source, a standard relationship in physics that applies to all electric fields in conductive media. At the surface of the metal, the field is measurable. At 1 centimeter of distance through moist soil, it has dropped to a tiny fraction of its surface value. At the distance of a plant stem or a flying insect approaching from above the soil surface, it is for practical purposes undetectable against the background electrical noise of the natural environment. The insect navigating toward your potato plant is not experiencing a coherent repellent field. It is experiencing the same complex electromagnetic background it encounters everywhere it flies. However, the genuinely fascinating adjacent science, the research that the viral videos are dimly and inaccurately gesturing toward, involves electric fields at a completely different scale. Studies published in applied entomology journals have documented that mosquitoes show consistent avoidance behavior when exposed to charged particles in their flight path, and that this avoidance is not a minor statistical effect, but a robust, repeatable response across multiple experimental conditions. A systematic review of published literature on insect electrosensitivity identified documented field avoidance behavior across 82 species in 17 different insect orders, ranging from beetles to flies to moths to thrips. The breadth of that finding suggests that sensitivity to electric fields is not an unusual feature of certain species, but a widespread characteristic of insect neurology with deep evolutionary roots. Just imagine what that finding implies for pest management, if the technology to exploit it were practical and affordable. Researchers in the Netherlands and in agricultural engineering departments at several British universities have tested exactly that possibility, developing high-voltage electric field screens for greenhouse use. These screens, which maintain a sustained charge measured in thousands of volts across an insulated barrier, have been shown to exclude flying insects, fungal spores, and airborne pollen from protected growing environments with considerable effectiveness. They are powered systems, requiring a continuous electrical supply and careful insulation to prevent hazard to workers. They are not a penny and a nail. At the same time, the distance between a functional high-voltage exclusion screen and a galvanic cell in garden soil is not merely a matter of engineering refinement. It is a difference of roughly 4 orders of magnitude in field strength, which means the buried metals would need to produce approximately 10,000 times more voltage than they actually do to generate effects at the scale the viral videos describe. No arrangement of copper strips and galvanized nails in garden soil produces anything approaching that field strength. And no published study in any peer-reviewed entomological journal has documented behavioral changes in any insect species attributable to a galvanic cell of the type the videos describe. The Auburn 2008 soil conductivity study, cited in several versions of the viral video with the same borrowed authority technique used for the fictional Cornell 1994 paper, does not appear in any verifiable research database. The pattern of the citation is identical: a real institution, a specific year, a precise-sounding measurement, and no traceable source document. Auburn University's agricultural research program is genuine and productive. The specific study being cited in its name is not. What Auburn and dozens of other land-grant universities have produced is something more useful: decades of documented research into the integrated pest management strategies that actually reduce pest pressure in real gardens across multiple seasons, and that research is where this video is heading next. The claim that the copper-zinc method was documented by a Penn State extension agent named Shoemaker in 1923, preserved in a physical archive, and quietly dropped from agricultural practice after 1948 when the chemical industry consolidated its grip on American farming, is constructed from real historical anxieties attached to an invented sequence of events. Search Penn State's agricultural extension records from the 1920s, and the agent named Shoemaker does not appear. The brother Yoder, who supposedly demonstrated the method to him, does not appear. The specific archive cited in the videos does not appear. What does appear when you look at what actually happened to American agricultural practice between 1945 and 1960 is a story dramatic enough to need no invented details whatsoever. Dichlorodephenyltric chloroethane, known to the world as DDT, was synthesized in 1874 by the Austrian chemist Othmar Zeidler, but its insecticidal properties went unrecognized for 65 years. In 1939, a Swiss chemist named Paul Hermann Müller, working for the Geigy Chemical Company in Basel, identified DDT's extraordinary effectiveness against a wide range of insects and recognized its potential for both agricultural and public health applications. Müller received the Nobel Prize in Physiology or Medicine in 1948 specifically for this discovery, an honor that reflected the genuine scale of what DDT appeared to offer at the time: a single compound that could protect crops, eliminate malaria-carrying mosquitoes, and control the louse-borne typhus that had devastated military populations in previous conflicts. The speed at which DDT entered American agriculture after the Second World War is difficult to overstate. By 1950, American farmers were applying it across millions of acres of cropland, and the chemical industry that had mobilized to produce explosives and chemical agents during wartime pivoted with remarkable efficiency to producing pesticides for a peacetime agricultural market hungry for exactly the kind of single-solution, permanent fix promise that DDT seemed to offer. The parallel to the viral garden videos is not accidental. The emotional appeal of a one-time application that ends your pest problem permanently has been the central marketing claim of agricultural chemistry since the moment DDT reached the farm supply shelf, and it was just as overstated then as it is now. What was genuinely lost in the decades following 1945 was not a metal in the soil secret. What was lost was institutional attention. University extension programs that had spent the preceding decades documenting crop rotation schedules, companion planting observations, mechanical pest exclusion methods, and the management of beneficial insect populations redirected their resources toward the testing and promotion of the new chemical tools. Research funding followed industry priorities, as it has always tended to do, and the unglamorous, labor-intensive, multi-season methods that had kept farms productive before the chemical era received progressively less documentation and less transmission to the next generation of farmers. Rachel Carson's Silent Spring, published in 1962, is the most famous account of what the chemical revolution cost in ecological terms, but Carson was documenting a crisis that agricultural entomologists and field naturalists had been observing and recording since the early 1950s. Bird population collapses near heavily sprayed orchards in the English countryside were noted in ornithological journals by 1953. Honeybee losses near treated American cornfields were being reported to extension offices by 1955. The resistance problem, the evolutionary acceleration of pest populations toward immunity against the compounds being used against them, was documented in the scientific literature within 5 years of DDT's commercial introduction. Beyond that historical reckoning lies a specific fact about resistance that reframes the entire pest management conversation. The Colorado potato beetle, the insect at the center of the viral copper story, has developed confirmed resistance to more than 50 individual insecticide compounds since 1952, a record unmatched by any other agricultural pest species. Each new compound introduced to control it produced selection pressure on the surviving population, accelerating the evolution of resistance in the next generation. The treadmill metaphor used in agricultural extension literature is precise. To stay in the same place relative to the pest, you must keep running, and the pace required increases with each new generation of resistant insects. No other dynamic in applied entomology illustrates more clearly why a one-time fix, chemical or metallic, is structurally incompatible with the biology of the problem it claims to solve. The methods that survive this period intact, not because they were hidden or suppressed, but because they were practiced by communities that never fully adopted the chemical alternative, were exactly the layered, multi-season practices documented in Lancaster County Amish farms and in the smallholder traditions of rural communities across Pennsylvania, Ohio, and the English West Country. Crop rotation disrupts the pest life cycle by removing the host plant from a location where eggs or pupae are overwintering in the soil. Diversified planting supports the predatory insect populations that regulate pest numbers without chemical intervention. Mechanical exclusion, physical barriers between the pest and the plant, at the moment the pest is most vulnerable, stops damage without producing resistance because it exploits a physical constraint rather than a biochemical pathway. These methods did not vanish after 1948. They were practiced continuously by the communities that had no access to or interest in the chemical alternative, and they were documented, if less prominently, by the extension researchers who continued to work in integrated pest management throughout the chemical era. What the viral videos have done is take the genuine drama of that history, the real post-war pivot away from ecological methods, the real costs of the resistance treadmill, the real productivity of communities that never made that pivot, and attach to it a metallic mechanism that those same communities do not recognize as the source of their results. The drama is real. The explanation is borrowed and misapplied. What actually accounts for the pest resilience of the best low-input gardens in Lancaster County and in the English countryside and in the urban plots of Boston and Manchester is a convergence of practices that each address a specific vulnerability in a specific pest's life cycle. Understanding those practices requires understanding the pest, and understanding the pest requires spending a season watching it rather than installing a fix and looking away. That shift from installation to observation, from one-time fix to ongoing practice, is the most significant thing separating a gardener who solves their pest problem from one who buys a new product every April. Pull a handful of healthy soil from a well-managed garden bed, and you are holding, among other things, trace quantities of copper and zinc in ionic form, dissolved in the soil water and available to plant roots through the same electrochemical uptake mechanisms that plants use to acquire nitrogen, phosphorus, and every other mineral nutrient they cannot photosynthesize from air and light. Copper and zinc are not exotic additions to a garden system. They are essential components of it, required in small but non-negotiable quantities for the biochemical processes that keep a plant structurally sound, metabolically active, and capable of mounting a defense against the insects and pathogens that probe it constantly for weakness. Copper's role in plant biology centers on a handful of enzyme systems, the most agriculturally significant of which involves lignin synthesis. Lignin is the compound that gives plant cell walls their rigidity and their resistance to physical penetration, and it is produced through a chain of enzymatic reactions in which copper-containing proteins called lacases and peroxidases play critical roles. A plant growing in copper-deficient soil produces thinner, weaker cell walls, a condition visible to a trained eye as a characteristic wilting and bleaching of new growth, and those thinner walls are physically easier for piercing and chewing insects to breach. The connection between copper nutrition and structural pest resistance is therefore real, documented in plant physiology literature, and worth taking seriously. Zinc operates through a different but equally fundamental set of pathways. It is a cofactor for more than 300 enzyme systems in plant metabolism, but its most directly relevant role for pest management involves auxin, the primary plant growth hormone. Zinc is required for the synthesis of tryptophan, the amino acid from which auxin is produced, and zinc-deficient plants show stunted, distorted growth that reflects disrupted hormonal signaling throughout the plant's development. Beyond growth regulation, zinc supports the production of phytoncides and other secondary metabolites that plants deploy as chemical deterrents against feeding insects. A zinc-adequate plant is chemically more complex and less nutritionally rewarding to a pest than a zinc-deficient one. What's more, the phrase that circulates in the viral videos, "A strong plant has no interest to the bug," is not merely poetic. It reflects a genuine principle in plant-insect ecology that researchers at several European agricultural universities have investigated in controlled conditions. Stressed plants, whether stressed by nutrient deficiency, drought, mechanical damage, or disease, emit a different volatile chemical profile than healthy plants, and many insect pests use those volatile signals as navigational cues when selecting feeding and oviposition sites. A plant broadcasting the chemical signature of stress is, in a measurable sense, advertising its vulnerability to the insects evolved to exploit it. A nutritionally adequate, structurally sound plant broadcasts a different signal, and that difference influences pest pressure in ways that are real and documentable. However, the critical word in that principle is adequate, and adequacy in plant nutrition is achieved through the soil, not through a buried metal strip. A copper strip pressed into garden soil does not dissolve and enter the soil solution at a rate meaningful to plant uptake. The process by which plants acquire copper from soil involves specific root exudates that solubilize copper ions from mineral compounds in the soil matrix, a biological process driven by root activity rather than by proximity to metallic copper. Placing metallic copper near a plant root is not equivalent to providing plant-available copper in the soil solution, and the claim that a penny feeds the bed reflects a fundamental misunderstanding of soil chemistry and plant nutrition physiology. The genuine version of this principle, the one with research behind it, is that soil health directly determines plant nutritional status, which directly influences pest susceptibility. A soil rich in organic matter, maintained with regular compost additions and covered with mulch to support microbial activity, cycles nutrients, including copper and zinc, through the biological processes that make them continuously available to plant roots. This is precisely what well-managed Amish gardens in Lancaster County achieve through their composting and cover cropping practices, and it is what any gardener can achieve through the same methods applied consistently over 2 or 3 seasons. The Ohio State 2016 study cited in the viral videos, which purportedly found a 22% increase in plant lignin content and a 41% reduction in pest pressure attributable to the buried metal system, does not appear in any verifiable research database under those parameters. The specific figures, like the Cornell 1994 and Auburn 2008 citations, are constructed with enough institutional specificity to borrow credibility without being traceable. What Ohio State's agricultural research programs have genuinely produced is extensive documentation of integrated soil fertility management and its effects on crop health, and those findings support the underlying principle without supporting the specific mechanism the videos describe. At the same time, systemic acquired resistance, a genuine and well-documented plant immune phenomenon, is what the viral videos are approximately describing when they talk about metals triggering a garden-wide defensive response. Systemic acquired resistance occurs when a plant that has been exposed to a pathogen or certain chemical elicitors activates a suite of defense genes throughout its tissue, producing increased concentrations of protective compounds including salicylic acid and pathogenesis-related proteins. This activation makes the plant more resistant not just to the initial threat but to subsequent attacks by a range of pathogens and some insects. It is a real phenomenon, documented in peer-reviewed plant pathology literature since the 1970s, and it represents genuine biology behind the intuition that a plant can be made more broadly defensive. What triggers systemic acquired resistance is not proximity to buried metal. It is exposure to specific biological and chemical signals, including certain beneficial soil microorganisms, dilute applications of compounds like salicylic acid itself, and in some documented cases, the controlled exposure to low-level pest pressure that primes the plant's immune system without overwhelming it. These triggers are available to any gardener through practices that cost nothing beyond time and attention, building soil biology through compost, allowing a measured diversity of insect life rather than attempting sterile exclusion of all arthropods, and growing plants in the nutritional conditions that allow their own defense systems to function at full capacity. The strong plant principle is real. The metal delivery system claimed for it is not. Stand in the pesticide aisle of any garden center in Boston or Birmingham in April and count the products on the shelf that were not available 10 years ago. The number is rarely fewer than a dozen, and the reason those new products exist is not that the old ones stopped being manufactured. It is that the insects they were designed to control stopped responding to them with the sensitivity that made them effective when they were first introduced. Resistance is not a theoretical concern in agricultural entomology. It is the dominant operational fact of chemical pest management, and it has been since the early 1950s, when entomologists first documented housefly populations in Illinois that survived doses of DDT sufficient to eliminate every fly in a naive population. The mechanism of insecticide resistance is elegant in the way that evolutionary processes tend to be elegant, which is to say it is simple, inevitable, and entirely indifferent to human preference. When a pesticide is applied to a pest population, the vast majority of individuals die. A small number survive, not because they were lucky, but because they carried genetic variants that conferred some degree of tolerance, whether through enhanced metabolic breakdown of the compound, reduced absorption through the cuticle, altered receptor sites that the compound can no longer bind, or behavioral avoidance of treated surfaces. Those survivors reproduce and their offspring inherit the resistance traits. Apply the same compound the following season and a larger fraction of the population survives. Within a small number of generations, which for insects reproducing multiple times per season means within a small number of years, the compound that once provided reliable control provides none. The Colorado potato beetle reached confirmed resistance to the first synthetic insecticides used against it within 5 years of their commercial introduction in the early 1950s. By the 1970s, it had developed resistance to organochlorine compounds including DDT, to organophosphates, and to carbamates, 3 chemically distinct classes of insecticide representing fundamentally different mechanisms of action. By the end of the 20th century, the confirmed resistance list exceeded 50 compounds, and researchers at Rutgers University in New Jersey, where potato production has long been economically significant. Documented populations in the mid-Atlantic states that showed measurable tolerance to neonicotinoid insecticides within 7 years of their introduction as the recommended alternative to the compounds that had already failed. Beyond that single species, the global picture of insecticide resistance compiled in the Arthropod Pesticide Resistance Database, maintained by Michigan State University, contains resistance records for more than 600 pest species across virtually every agricultural system and every chemical class currently in use. The database grows every year, not because new species are developing resistance for the first time, but because existing resistant populations are spreading geographically, acquiring resistance to additional compounds, and appearing in crops and regions where they were not previously recorded. The treadmill metaphor is precise in a way that makes it uncomfortable. The pace required to stay ahead of resistance has been increasing continuously since the mid-20th century, and the cost of running it falls not on the chemical industry, but on the farmer paying for each new product. Here is the thing. The viral garden videos understand this reality at the level of feeling even if they misrepresent it at the level of fact. The gardener, who has spent 4 seasons buying successive generations of pesticide products and watching each one work less reliably than the last, is experiencing the resistance treadmill in miniature, on a backyard scale, and the exhaustion that produces is genuine. The promise of an exit from that treadmill, a method that pests cannot develop resistance to because it is not a chemical pathway but a physical or electrical one, is not an irrational hope. It is a logical response to a real problem. The error is not in wanting an exit. The error is in accepting an exit that does not lead where it claims. Physical exclusion methods, the category of pest management that genuinely cannot be overcome by evolutionary resistance because they exploit physical constraints rather than biochemical pathways, represent the real exit from the treadmill for the specific pest problems they address. A floating row cover placed over a crop at the moment of vulnerability does not become less effective as the season progresses because the pest population adapts to it. The squash vine borer cannot lay its eggs on a stem it cannot reach, regardless of how many generations of borers have encountered row covers before it. The cabbage moth cannot deposit eggs on a plant concealed beneath a physical barrier. No genetic variant confers the ability to pass through a material that physically excludes the insect's body. What's more, the timing of physical exclusion is where the genuine science produces results that feel almost as dramatic as the viral promises, because the difference between a row cover applied at the right moment and one applied a week too late is the difference between a healthy crop and a destroyed one. Squash vine borer moths in the northeastern United States and in comparable climates in the English Midlands begin laying eggs in late June and continue through July, targeting the base of squash stems just above soil level. Floating row cover applied as soon as transplants go in the ground, before the first moths appear, and maintained through the egg-laying period provides near-complete protection. The same cover applied after the first eggs are laid provides nothing, because the larvae are already inside the stem where no barrier can reach them. Pheromone traps, which attract male moths of the target species using synthetic versions of the female's mating signal, give the gardener something the viral metal system never provides: information. A pheromone trap for squash vine borer placed in the garden in mid-June tells you with precision when the moths are flying in your specific location in your specific season, allowing you to time the application and removal of row covers to the actual biology of the pest rather than to a generic calendar recommendation. That information, combined with the physical barrier, represents a genuinely integrated response to a specific pest that no amount of buried copper or galvanized nails approaches in effectiveness. And the cost of a pheromone trap is comparable to the cost of the copper and zinc the videos ask you to buy. The deeper point, which connects this specific pest management conversation to a larger truth about how durable solutions work in any complex biological system, is that resistance to physical and behavioral controls is not impossible, but it is orders of magnitude slower than resistance to chemical ones, because the selection pressure operates on traits that are physiologically and behaviorally fundamental, rather than on single enzyme systems that can be modified by point mutations. A pest population cannot evolve the ability to fly through solid fabric in the way it can evolve an enzyme variant that breaks down a specific molecular compound. That asymmetry is the structural reason why the exit from the resistance treadmill runs through exclusion, timing, and variety selection, rather than through any single compound or any single installation, metallic or chemical. The most valuable sentence in any honest pest management conversation is also the least glamorous one. Different pests require different responses, and no single method addresses all of them. That sentence kills the viral video format because it refuses the promise of a universal fix. And universal fixes are what drive clicks in April when the seed catalogs have arrived and the optimism of a new growing season has not yet been tempered by the first wave of damage. But that sentence is also the one that separates a gardener who solves their pest problems across multiple seasons from one who buys a new solution every spring and faces the same losses every summer. Start with the squash vine borer, because it is the pest that defeats more first and second-year gardeners in the northeastern United States than any other. And because the gap between what actually controls it and what the viral videos promise is particularly wide and particularly costly. The adult squash vine borer is a moth, Militia cucurbitae, that mimics a wasp in its coloring and flight pattern with enough accuracy to startle gardeners who encounter it for the first time. It flies during daylight hours, which is unusual for a moth, and it lays its eggs individually at the base of squash stems in late June and July. The larva that hatches from each egg bores directly into the stem and feeds from inside, causing the sudden and complete wilting that gardeners often misdiagnose as drought stress until they cut the stem open and find the cream-colored larva inside. Floating row cover, a lightweight spun-bonded polypropylene fabric that transmits roughly 85 to 90% of available light while physically excluding insects, is the single most effective tool against squash vine borer available to a home gardener at reasonable cost. Applied immediately after transplanting or germination, before the first moths of the season appear, and secured at the edges with soil, rocks, or clips so that no gap exists at ground level, it provides near-complete protection through the egg-laying period. The fabric must be removed when the female flowers open to allow pollinator access, and this is a timing decision that determines whether the method succeeds or fails. Remove too early, and the moths reach the stems before egg-laying is finished. Remove too late, and the flowers close unpollinated and no fruit sets. A pheromone trap placed in the garden from the first week of June tells you when the moths are actively flying in your location, giving you the information needed to make that timing decision accurately rather than by guesswork. However, the row cover approach carries a critical prerequisite that the viral videos never mention, and that extension services emphasize consistently. It only works where squash was not grown in the same location the previous season. The squash vine borer overwinters as a pupa in the soil, typically within 5 centimeters of the surface in the area where the previous year's vines grew. Planting squash in the same bed the following spring places the new plants directly above an emerging population of adult moths that will be present before any row cover is in place. Rotating squash to a new location each year, combined with the physical barrier, removes both the overwintering population and the egg-laying opportunity in a single integrated step. Variety selection is the second tool, and it is the one that delivers results across the full growing season rather than only during the egg-laying window. Butternut squash shows substantially lower susceptibility to squash vine borer than summer squash or Hubbard varieties, partly because its stems are harder and drier at the base where the larva attempts to enter, and partly because the larva's feeding damage, while present, rarely severs the vascular tissue completely in the way it does in the softer stems of zucchini and pattypan types. Cucumbers and melons, members of the cucurbit family but not preferred hosts for Militia cucurbitae, can fill the garden space where susceptible squash would otherwise grow and produce a harvest through the borer season without requiring the same intensive management. That is not a workaround. It is a genuine season-long solution available to any gardener willing to adjust what they plant rather than only how they protect it. For slugs, the Honest toolkit looks different from the copper tape approach in ways that matter for real garden conditions. Water glass sodium silicate solution available from pharmacy suppliers and some garden centers, painted onto the rim of containers and raised bed frames, creates a dry, crystalline surface that slug mucus cannot bridge effectively. The semi-field study that found copper foil merely delayed slug passage found that water glass completely blocked it for the duration of the trial. Beer traps, shallow containers sunk to ground level and filled with inexpensive beer, exploit the slug's attraction to yeast fermentation products and provide genuine population reduction when placed at the perimeter of vulnerable beds and emptied every 2 to 3 days. Neither method is as cinematically satisfying as a buried metal system, but both produce measurable outcomes in conditions where copper tape has been shown to fail. Beyond exclusion and barriers, the management of the garden environment itself is where the most durable long-term pest reduction accumulates. Slugs require moisture and shelter to survive the daylight hours, and a garden bed that is watered in the morning rather than the evening, that is kept free of the dense ground-level debris where slugs shelter during the day, and that has its soil surface disturbed periodically to expose eggs to desiccation and predation, supports a substantially smaller slug population than one that provides ideal daytime shelter and nighttime moisture simultaneously. These are not dramatic interventions. They are observations about slug biology translated into watering schedules and tidying habits, and they compound in effectiveness across seasons in a way that a one-time installation cannot. Aphid management sits in a third category, one where neither copper nor zinc nor any physical barrier is relevant, because aphids arrive by flight or by ant farming, establish colonies on the growing tips and undersides of leaves, and are controlled most effectively by the beneficial insects that evolved specifically to consume them. A single adult ladybird, known in North America as a ladybug, consumes between 200 and 5,000 aphids across its lifetime, and a lacewing larva is equally voracious. These insects are present in any garden that has not eliminated them through broad-spectrum pesticide use, and their populations build fastest in gardens that provide them with the overwintering habitat, the nectar sources, and the undisturbed ground cover they need to establish across seasons. A hard spray of water from a garden hose directed at aphid colonies on the undersides of leaves physically dislodges the majority of a colony without harming the plant or the beneficial insects, and it costs nothing beyond the time it takes to do it. What connects all of these methods is not a metal in the ground or a battery under the soil. It is the habit of looking at each pest as a specific organism with a specific life cycle, specific vulnerabilities, and specific points at which an intervention costs the least effort and produces the most reliable outcome. That habit is the genuine inheritance of the low-input agricultural tradition that the viral videos borrow from without accurately describing, and it is available to every gardener regardless of their budget, their plot size, or how many seasons of damage they have already endured. Walk into any hardware store in Philadelphia or Leeds on a Saturday morning in early April, and you will find everything you need to implement the methods this video has been building toward, and the total cost will be lower than the copper and zinc kit the viral videos recommend. That is not an accident of pricing. It is a consequence of the fact that the methods with the strongest evidence behind them rely primarily on timing, observation, and inexpensive materials, rather than on proprietary installations that require a specific product to execute. The most expensive thing you will spend on genuine pest management this season is probably not money. It is attention paid at the right moment. The physical shopping list for a gardener managing a typical backyard plot with raised beds or in-ground rows covering roughly 20 to 30 square meters is short. Floating row cover fabric, sold in rolls of varying width at most garden centers and online suppliers, costs between $15 and $25 or pounds for a quantity sufficient to cover 3 or 4 bed lengths with overlap to spare. A pack of wire hoops or bent sections of heavy-gauge wire to hold the fabric off the plant surface costs another $5 to $10. 2 or 3 pheromone traps for the specific pests most relevant to your planting, squash vine borer in the Northeast, cabbage moth across most of temperate North America and Britain, at another $10 to $15 combined. A bottle of sodium silicate solution for water glass barriers around containers and raised bed rims costs roughly $8 to $12 from a pharmacy or garden supplier. Beer for slug traps costs whatever beer costs, and the slugs are not particular about the brand. Copper tape is not on that list, and the reason is specific rather than categorical. Around an isolated container in a dry period, a clean 2-inch or wider copper tape barrier offers a genuine, if partial and maintenance-dependent, supplementary deterrent against small slug populations. And if you already own copper tape from a previous season, it is worth using in that application. What it is not worth doing is purchasing copper tape as a primary pest management strategy. Burying it in open soil where patina formation and debris bridging will render it ineffective within 1 to 2 seasons, or extending its application to pests other than slugs and snails, for which it has no documented mechanism of action. Galvanized nails in stakes or soil should be omitted entirely. There is no peer-reviewed evidence for any pest management effect attributable to zinc in that form or placement, and the money and time spent on them is more productively directed elsewhere. The week-by-week arc of a first season using these methods looks nothing like the dramatic overnight transformation the viral videos promise, and it is important to say that clearly rather than substitute one unrealistic timeline for another. What it looks like is a gradual accumulation of advantages that compound as the season progresses, and as your understanding of the specific pest pressures in your specific garden becomes more precise. The first 2 weeks after transplanting or germination, with row covers in place and secured, produce a visible and immediate result. The plants grow without interruption from the flying insects that would otherwise be probing them for egg-laying sites. That absence of damage is quieter than a dramatic pest collapse, but it is real and it is measurable in the plant's growth rate and structural condition at the end of the covered period. By the 4th and 5th weeks, when pheromone trap catches tell you whether moth flight has peaked or is still building in your area, you're making a timing decision based on actual data from your actual garden rather than from a generic calendar. That decision, remove the cover now or wait another week, is the kind of precise, biology-grounded choice that separates gardeners who consistently succeed from those who follow instructions without understanding what the instructions are responding to. Removing the cover at the right moment, when female flowers are opening and moth flight is declining, allows pollination without surrendering the protection the cover provided through the most critical egg-laying window. At the same time, the slug barrier work is producing its own quieter accumulation of results across those same weeks. Water glass applied to raised bed rims at the start of the season, renewed after heavy rain because the crystalline surface gradually weathers, maintains a physical barrier through the cool, wet conditions of spring when slug pressure is highest, and plant seedlings are most vulnerable to the kind of grazing damage that can remove a seedling entirely in a single night. Beer traps checked and refilled every 2 to 3 days during peak slug activity, which in most temperate climates runs from April through June and again in September and October, capture adults before they lay the egg clusters that will produce next season's population. This is not a one-time fix. It is a maintenance rhythm, and the gardener who builds that rhythm into their seasonal routine finds that by the 3rd season, the slug population in their specific beds is measurably smaller than it was in the first, because the trapping is continuously reducing the breeding population rather than merely protecting individual plants. The aphid situation, managed through a combination of hard spray dislodging and the preservation of beneficial insect habitat, follows a different arc again. The first season is often the hardest because a garden transitioning away from broad-spectrum pesticide use has a depleted beneficial insect population that is not yet recovered to the density needed to regulate aphid outbreaks autonomously. Expect to intervene manually with water sprays more frequently in the first year. By the second season, ladybirds and lacewings will be overwintering in greater numbers in undisturbed areas of the garden, emerging earlier in the spring to track the first aphid populations as they establish. By the 3rd season, in a garden that has consistently provided overwintering habitat and nectar sources through flowering herbs and umbellifers like dill and fennel allowed to reach full bloom, the beneficial insect population typically keeps aphid pressure below the threshold of visible crop damage without manual intervention. You won't believe this, but the most common response from gardeners who have followed this kind of integrated approach across 2 or 3 full seasons is not satisfaction with any single method. It is surprise at how much of the anxiety that drove them to the viral videos in the first place has simply dissipated, not because every pest has been eliminated, but because each pest has become a recognizable, manageable part of a system they understand. The squash vine borer is no longer a catastrophe. It is a moth that flies in late June and can be excluded, and they know exactly what to do about it and exactly when to do it. That is a different relationship with the garden than the one produced by installing a fix and hoping it holds. The neighbor who has not had a serious squash pest problem in 15 years is not, in the honest version of that story, the person who buried copper and zinc in the right configuration. They are the person who tried resistant varieties, learned the borer's flight timing through several seasons of observation, started using row covers at the moment of transplanting, and rotated their cucurbit beds consistently enough that the overwintering pupa population in any given location never built to the density that produces catastrophic losses. That is a 15-year story. It is also a genuinely repeatable one, available to any gardener willing to spend the first 2 seasons learning what the third season will reward. There is a genuine grievance at the center of every hidden knowledge gardening video, and it is worth taking seriously before examining what the videos do with it. The grievance runs roughly like this. The methods that genuinely work over the long term, crop rotation, diversified planting, mechanical exclusion, beneficial insect habitat, soil biology management, are unglamorous, require sustained attention across multiple seasons, and cannot be packaged into a product that generates recurring revenue. The methods that generate recurring revenue, bottled pesticides, single-use traps, proprietary soil amendments, are sold aggressively every spring through retail channels, magazine advertising, and increasingly through the same social media algorithms that promote the viral garden videos. That asymmetry between what works and what gets promoted is real, and the anger it produces in gardeners who have spent money on products that failed them is legitimate. What the hidden knowledge format does with that legitimate grievance is a specific and rhetorically sophisticated move. It takes the real asymmetry between unglamorous effective methods and aggressively marketed ineffective ones, and it reframes it as suppression. The story shifts from effective methods are underpromoted because they don't generate recurring sales to effective methods were deliberately buried by an industry that profits from your annual pesticide purchase. That shift from neglect to conspiracy is emotionally satisfying in a way that the accurate version is not, because it provides a villain, a narrative of deliberate harm, and a sense of participating in resistance by sharing the video. It also, not coincidentally, positions the video's creator as the brave truth-teller who recovered the suppressed knowledge at some personal cost of research and effort. The invented archives serve this narrative function precisely. A Penn State Extension report from 1923, found in a physical archive by a researcher willing to dig where others did not, is a story about effort and discovery that validates the viewer's sense of receiving something genuinely rare. The fictional nature of that archive does not reduce its narrative effectiveness for viewers who never check the citation, and most viewers do not check citations. What it does is create a specific vulnerability, the comment from the viewer who did check, who searched Penn State's digital agricultural extension records and found no agent named Shoemaker and no Brother Yoder and no 1923 copper report, and who says so in terms that are visible to every subsequent viewer and that the channel cannot rebut because the rebuttal does not exist. Just imagine the difference in that comment section if the manifesto were built on the true history instead of the invented one. Pierre-Marie Alexis Millardet, walking through a Bordeaux vineyard in 1879 and noticing that the vines painted with copper sulfate to deter grape thieves were free of downy mildew. That is a documented, cinematic, verifiable origin story that does the same emotional work as any invented archive without creating a single falsifiable vulnerability. The post-war pivot of American agricultural extension toward chemical solutions at the expense of integrated methods. That is a real and documented shift in institutional priorities that carries genuine dramatic weight. Rachel Carson, finishing the manuscript of Silent Spring in 1962 while herself seriously ill, knowing the chemical industry would attempt to discredit both the book and its author. That is a story of genuine courage attached to a genuine suppression of inconvenient evidence that requires no invented agent named Shoemaker to make it compelling. Beyond that, the hidden knowledge format's deepest structural problem is not that it invents sources. It is that it offers a shortcut as the payoff for the suppressed knowledge, and shortcuts are what the format claims to be exposing as a failure mode of the mainstream approach. The viral video says, in effect, the industry wants you buying products every year, but here is the one-time installation that frees you from that cycle forever. That promise replicates the structure of the thing it critiques. It substitutes one product-shaped solution, the copper and zinc kit, for another, the annual pesticide purchase, while claiming to offer something categorically different. A viewer who recognizes that substitution, who notices that the liberation being offered is itself a purchase, has identified the core irony of the format. The version of the hidden knowledge manifesto that is both honest and more persuasive makes a different promise. It does not offer a product, it offers a framework. The understanding that pest management is a biological problem requiring biological thinking, that the life cycle of each pest contains specific vulnerabilities that can be exploited through timing and physical exclusion without generating resistance, and that the knowledge required to exploit those vulnerabilities is genuinely available, documented in extension literature that is publicly accessible and free, and has been practiced continuously by farming communities who never abandoned it for the chemical alternative. That framework is harder to sell in a thumbnail. It is substantially harder to debunk in a comment section because it is true. What's more, the framework actually delivers the emotional payoff that the hidden knowledge format promises but fails to provide. When a gardener applies floating row cover at the right moment and walks out the following week to find their squash plants unmolested, while their neighbors' plants are showing the first signs of vine borer damage, the satisfaction of that outcome is genuine and specific in a way that burying a metal strip and hoping for the best never produces. The knowledge that worked is knowledge about the pest's biology, the moth's flight timing, the egg-laying behavior, the larva's entry point, and the physical constraint that prevents access to that entry point. That knowledge compounds across seasons. It transfers to related problems. It makes the gardener who holds it more capable each year rather than equally dependent on the next product. The marketing of single-product fixes, whether chemical or metallic, gets less attention than it deserves as the structural problem underlying both the pesticide treadmill and the viral garden video economy. Nobody profits from selling crop rotation. Nobody runs a sponsored post promoting the insight that moving your squash beds each year disrupts the overwintering pupa population in a way that reduces adult moth emergence the following June. The extension researchers who documented these methods receive no royalty when a gardener applies their findings successfully. That invisibility of unglamorous effective knowledge is the real hidden knowledge story, and it is available to any channel willing to tell it honestly rather than dress it in fake archives and buried metals. The call to carry that honest version of the story forward, to share it specifically because it is the version that holds up to scrutiny in the comments and that produces real outcomes in real gardens, is a stronger and more durable ask than the request to share a secret that someone else will debunk by next Tuesday. A community built around verified, extensible, season-tested knowledge grows differently from one built around a single viral claim, because the knowledge keeps delivering and the community keeps returning to report on what it delivered. That dynamic, viewers returning to say, "This actually worked, here is what happened," is the signal that distinguishes a channel producing durable value from one producing a single spike. Here is the verdict this video promised you at the start, delivered as precisely as the evidence allows. Copper has a genuine, moderate, documented repellent effect against slugs and snails through an electrochemical mechanism involving their mucus, and that effect is real under dry laboratory conditions with clean, wide barriers against small specimens. In a real garden with real weather, real adult slugs, and real organic debris bridging the barrier, the most rigorous garden-realistic study conducted to date found no measurable reduction in plant damage. Both of those things are true simultaneously, and the gap between them is not a reason to dismiss copper entirely. It is a reason to use it precisely, as a supplementary measure around isolated containers in dry periods, cleaned regularly, and never as a standalone solution against any pest other than mollusks. Zinc, in the form of galvanized nails placed in soil or stakes, produces no documented pest management effect through any verifiable mechanism. The Spannungsfeld tension field, the Gardeners battery concept, and the claimed Auburn 2008 soil conductivity study that supports it do not survive contact with basic physics or basic database searching. The voltage produced by a copper-zinc galvanic cell in garden soil is real, but orders of magnitude too small to generate behavioral effects in insects at any distance from the metal surface. The genuine science of electric field insect repellents is fascinating, and the documented effects across 82 species in 17 insect orders are real, but the systems that produce fields strong enough to matter are high-voltage powered installations, not a coin and a nail. The Amish of Lancaster County genuinely do practice productive, low-input agriculture that achieves real pest resilience across multiple seasons. What accounts for that resilience is crop rotation, diversified planting, composting, mechanical exclusion, and the layered biological complexity of a well-managed soil ecosystem. None of the peer-reviewed documentation of Amish agricultural outcomes attributes that resilience to buried metals, because none of the farmers practicing those methods credit buried metals as the primary mechanism. The viral videos borrowed the credibility of a real community and a real set of results, and attached to them an explanation that the community's own practices do not support, and the research record does not verify. The Cornell 1994 study producing a 96% pest reduction figure does not exist in any verifiable form. The Penn State 1923 Shoemaker Archive and Brother Yoder do not exist in any verifiable form. The Ohio State 2016 Lignin and Pest Reduction Study with the specific figures cited in the viral videos does not exist in any verifiable form. These citations follow an identical pattern: a real institution, a specific year, a precise-sounding result, and no traceable source document. That pattern is the most reliable single indicator that content has been manufactured rather than researched, and recognizing it is a skill that protects you from wasting both money and growing seasons on methods that cannot deliver what they promise. What does exist in publicly accessible extension literature from Penn State, Cornell, the University of California, the Royal Horticultural Society, and agricultural universities across Britain and the United States is detailed, replicated, season-tested documentation of the methods that actually reduce pest pressure in real gardens across multiple years. Floating row cover timed to the squash vine borer's flight window provides near-complete protection against a pest that destroys more cucurbit crops in the American Northeast than any other single organism. Pheromone traps give you the timing information that makes that protection precise rather than approximate. Resistant variety selection removes the vulnerability that requires intensive management in the first place. Water glass barriers outperform copper tape against slugs in realistic outdoor conditions. Beneficial insect habitat built over 2 to 3 seasons reduces aphid pressure below the threshold of visible damage without manual intervention. These methods work. They are free or inexpensive. They are available to any gardener regardless of plot size or experience level. Beyond that practical verdict lies a larger point worth carrying into every gardening decision you make this season and the ones after it. The promise of a universal, permanent, one-time fix for a biological problem is the structural signature of a claim that will not survive a full-growing season of testing. Biology is not a problem to be solved once. It is a system to be understood and worked with continuously, and the understanding compounds in a way that the installation never does. A gardener in their 3rd season of timing row covers to pheromone trap data, rotating beds, managing slug populations with water glass and beer traps, and building beneficial insect habitat through undisturbed overwintering areas and flowering herbs is not fighting pests the way they were in their 1st season. They are managing a system they understand, and the gap between those two experiences is the gap between frustration and genuine competence. The comment section below this video is where that competence gets tested and shared, and it is where this investigation continues. If you have buried copper or zinc in your garden and watched what happened across a full season, say so specifically. What pest, what placement, what result, what the weather was doing. If you have used floating row cover against squash vine borer and timed it to trap data, report what the timing looked like in your location and what the outcome was. If you have a slug problem that copper tape failed to solve and you tried something else that worked, that information is worth more to the gardeners reading these comments than any claimed study from any invented archive. The next video in this series applies the same investigative treatment to a specific claim you will have encountered if you have spent any time in gardening communities online. That wood ash spread around plant bases repels slugs, deters cabbage root fly, and raises soil pH enough to suppress clubroot in brassicas, all simultaneously, all permanently, for the cost of emptying your fireplace. Some of those claims have genuine research behind them. Some of them do not. At least one of them is true in a way that is more specific and more conditional than the viral version presents, and at least one collapses entirely on contact with a realistic outdoor test. The verdict on wood ash will follow the same structure as this one. Here is the claim, here is what the lab found, here is what a garden realistic study found, and here is what you should actually do this weekend based on what the evidence genuinely supports. Subscribe if you want that verdict when it arrives, and share this video specifically with the gardener in your life who is about to spend $25 on copper flashing and galvanized nails on the strength of a viral recommendation. The most useful thing you can do for them is not tell them the viral video is wrong. It is show them what the investigation actually found. Let the evidence speak in the specific and citable terms this video has tried to provide, and give them something better to do with that $25 in that weekend than bury metals that the research record cannot support. The garden is waiting. The season is shorter than it feels in April. Spend it on what works.